Today we will start with kinematics. Kinematics is a branch of mechanics where we study motion of a point or a particle and we describe the motion without describing what causes the motion. So, when we study kinematics, we do not go in the details of what is causing the motion, but we just analyze the motion. But before we start with kinematics, let us look at some basic mathematical concepts. You will realize that while studying physics, we do need the help of mathematics, and the mathematical concepts which we will talk about, you will study details about them in maths, but here we will introduce some of the concepts as and when we need them. So, we are talking of motion of a point, and we will restrict our discussion to planar motion. That means, a particle is moving in a plane. So, here to describe the position of a point, we use what we call as a coordinate system. And what we do is, we take two mutually perpendicular directions, let us say one of them is x, the other is y. So, we call them the two Cartesian axes, and they are x and y, and these axes are mutually perpendicular. That means, they are at an angle of 90 degrees to each other. Now, the intersection of these is called the origin, represented by O. Any point P which is at a location here is described by what we call as the coordinates of these points x and y. And what we mean by x is that if we look at the x distance, the amount of distance this point is from the origin along the x axis, that is given by x, and the distance the point is along the y axis is given by y. So, x comma y are called the coordinates of the point P. So, let us write this: the position P of a point is given by the coordinates x comma y. Now, clearly, as the point P moves, that means it is moving along some path, then the values of x and y will change, and this is the analysis of this is what we will do when we talk of kinematics. Now, there is another term which we define, this is the point P. If we draw a line segment from O to P, then this O to P, which is a directed line segment from origin to the position of P, this OP is what we call as the position vector. Now, this is a directed line segment, because what we realize is the quantity OP has two quantities. One is the length OP, which is also called the magnitude of the vector, and the second thing is the direction of OP. With the same length, if I travel along a circle, I can get different point P which have the same length, but to give the precise direction of point P, we then give the we mark from O to P, and this direction is what gives us the directionality of the vector. Therefore, you can think of a vector as a quantity which has two characteristics. One is the magnitude, which in case of a position vector is the length, and the second is the direction, and together both of these they define a vector, and we can uniquely then define a position vector with these quantities. Let us also see some concepts of what we call as calculus, and two, you could call them branches of calculus. First we will see elements of differential calculus, and once again what we are describing here is very limited mathematics. This is not to be taken as a class in maths. The mathematical details of these and more involved mathematical problems, concepts you will get to see in your maths course. So, to understand the first we have what we call as a concept of a derivative. In differential calculus is all based on derivatives. Now, suppose we have a line which is varying with x. So, this we call as y is equal to function of x. So, we define a curve y is equal to function of x. That means, for different values of x we have different values of y, and when we join them together we get this curve which we call as y is a function of x. Now, let us look at 2 points P and Q on this curve. So, we have a same curve, there are 2 points P and Q on this curve. Now, let us say the coordinates of point P are x and y, the coordinates of point Q is located at a distance delta x away from P in the x direction, and it is located at a distance delta y away in the y direction from point P. So, therefore, the coordinates of point Q, so coordinates of point P are x comma y, and coordinates of point Q, the x coordinate will be x plus delta x and the y coordinate is y plus delta y. So, these are the coordinates. Now, if we look at a straight line joining PQ, then if we look at the make a right triangle like this, that means we continue P up till where Q, the extent of Q along x axis, and then go vertically up to point Q, and if this angle is theta, then we can clearly see that tangent of theta will be equal to delta y upon delta x. So, now what we say is, if the point Q approaches point P, so we let Q approach P, which means we are now taking it closer and closer to point P, but it does not exactly go to point P. So, this we say that Q approaches P, which we will mean we say that delta x approaches 0, and we will have delta y, which is the distance along y, this will also approach 0, but delta y by delta x the division of these two, this will not approach 0 in a general case. In a specific case it could go to 0, but generally delta y by delta x, this is a small quantity, this will not approach 0. And here what you will see is the straight line PQ, this will approach tangent to the curve at point P. So, the line PQ approaches the tangent of the curve. Now, if we denote slope of the line, and slope of the line is again something which you will see in coordinate geometry, and so this in mathematics course, if we denote this slope of the line by m, then what we have is the slope of the line m is equal to delta y by delta x in the limit delta x goes to 0. So, now what we do is we define the derivative of a function y with respect to x, where y is equal to f of x. This is defined as, so we use the symbol dy by dx, and this is written as, we write it as derivative of f of x with respect to x. This will be equal to function of x plus delta x minus its value at x. So, this is the value of y at x plus delta x, which is delta y, minus f of x, which is y, divided by delta x, and this we take and this we call as the process of limit as delta x tends to 0. So, this we write as in the limit delta x going to 0, and this is termed as the derivative of the function at the position x. And physically this is equal to the slope, or this is equal to the slope of the tangent at that point. So, this is how we define derivative. And once again, more of this concept of derivative you will see when you do your the mathematics course. Now, if we have there are some simple formulas for derivatives which we may need. So, I will just give you some of these formulas. So, suppose we have two functions u of x and v of x. There are two functions, just as we had f of x, there are two of these. Then what we have is derivative of u plus v is equal to the sum of the derivatives. So, any quantity which is defined as sum, you can take the derivative of individual functions, add them up. For product we have a different rule. If we have the product of u and v, then the derivative of this is given as u times dv by dx plus v times du by dx. So, this does not follow the same rule as we had for addition, but the derivative rule for product is in this form. And then we have a derivative rule for a division for quotients, d of u by v divided by dx, or derivative of u by v is equal to 1 over v square du by dx minus u times dv by dx. And once again these derivations you will do in detail in your maths course. Now, if we have a power, if we have x to the power of n, then the derivative of x to the power of n with respect to x is given by n times x to the power of n minus 1. So, and if we have a function u, if u is equal to u of x, then what we have is then derivative of u to the power of n with respect to x is given by n times u to the power of n minus 1 times du by dx. And actually this formula which I have done, this is a generalized form of a formula which we have, which is called the chain rule. And in chain rule what we have is, if we have a function f which is a function of u, and u is equal to u of x. So, now here if we want to find, f is known to us as a function of u, let us say f is equal to u square, and u is equal to 2x. So, u is a function of x, f is known as a function of u, and if we want to now find the derivative of f with respect to x. Now, here notice we do, f is known as a function of u and u is known as a function of x. So, here what we do is, this is given by, first we differentiate f with respect to u and then we multiply it by the derivative of u with respect to x, and this is what is termed as the chain rule. This is often, it will come out very handy, and you should keep this in mind, that is how we use this. Now, we also have a couple of trigonometric functions. Derivative of sin x with respect to x is equal to cosine of x, and derivative of cos of x with respect to x, this is equal to minus sin x. There are formulas for tangent and cotangent, sec, etc. They can be all worked out from here, and using some of the rules we have done, we have the product rule. So, for finding the derivative of tangent, we can take sine divided by cosine and work it out. So, these things can, so these are some of the differential calculus which may be needing right now. There will be more of maths we will be needing, but those we will see as and when we need. The other thing which we need slightly is some elements of what we call as integral calculus. And here, if we have this problem, if we have a function f of x, and what we want to find is the area between f of x and the x axis when x is equal to a, or between x is equal to a and x is equal to b. That means, at this point this is the x axis, x is equal to a, at the other point x is equal to b, there is a function f x. We want to find the area of this shaded portion which lies between the x axis and f x, and on the left side we have the limit x is equal to a, on the right side it is x is equal to b. Clearly, if f of x is a straight line, then the area will be the area of a rectangle, which we can easily work out. But how do we work this out if this is a general curve f of x? And to find this area between f of x and a b and the x axis from a to b, what we do is we divide this area. So, we have this curve f of x, this is the x axis, this is x is equal to a, this is x is equal to b. We divide this distance from a to b in many small intervals. Let us say a position, intermediate position is given by xi, and each of these interval has a length delta xi. So, now that means I am looking at xi and the next interval delta xi. So, this area of this small portion, I write this area as delta ai. So, delta ai will be equal to, this area will be equal to this height here, which is f of whatever is here, that is f of xi multiplied by delta x. So, this is the width of the strip and this is the height. So, product of these two gives me the area of the strip. So, the total area, this will be equal to summation of all these delta AIs. So, that means I make all these areas here and add them up, that will give me the total area. So, what we have is, if I write this, the total area, this will be, this is a symbol for summation capital sigma delta AI. So, this will be equal to sum of I going from 1 to n f of xi delta x. Now, if we want all this summation of area to match the exact area, that means we should make these rectangles smaller and smaller. So, therefore, what we to do this, what we say is, if n tends to infinity, that means n becomes very large, then the summation sign which we have, we call this as the integral, and we use a symbol which is like an elongated S. This is the symbol of integral. So, this is when sigma, when n tends to infinity, we call that as the integral, and what we say is the area is the integral of f of x, and delta x we write it as dx, and this goes when x is equal to a to x is equal to b. And right now here, to explain to you, I have written x is equal to a and x is equal to b, but normally we write it as integral from a to b f x dx, and this is what we call as the integral. So, integral of a curve is the area under the curve between the lower limit and the upper limit. This is the first limit here, this is the lower limit of integration, and this is called the upper limit of integration. So, and such an integral, this what we have done when we have area under the limits, this is called a definite integral, and this definite integral is the area under the curve. Now, what we can also show is that integration is the inverse of differentiation, which means that if we have a function g of x such that the derivative of g x is equal to f of x, then g of x is equal to the integral of f x with respect to x. So, in that sense, integration is inverse of differentiation, because if dg by dx is equal to f, then integral of f is equal to g. And when we write some, this we can write, if we say integral from a to b f x dx, this will turn out to be, this is equal to g of x, and in terms of when we put definite integration, we put limits here, then this will be equal to gb minus ga. So, and this is how we put the limits in integration. If we just integrate it and leave it in form of a function, then the integral function is evaluated up to an arbitrary constant. And if we look at some of the, again some of the formulas for integral functions, this you can see in your, in any book, and they take the form integral of x to the power of n with respect to x, this is equal to x to the power of n plus 1 divided by n plus 1 plus a constant. Any of these indefinite integrals where the limits are not put, we always put it up to an arbitrary constant, and in this formula n is not equal to minus 1, because if n is equal to minus 1, this will become 0, and this does not work for n is not equal to minus 1. Then we have another formula, integral over 1 over x dx, that means this is the case when n is equal to minus 1. This is given by a function called the logarithmic function natural log of x. You may not know too much about this function right now, but you will see this later on in some of your maths courses, and when we need it here we will explain this. So, and once again, because these are indefinite integrals, we put an arbitrary constant. Two more things when we look at, we need these integral of sine of x dx will be equal to minus cosine of x plus c, and integral of cosine of x dx, this will be equal to sine of x plus c. And these functions, these two formulas you can directly get from the inverse rule which I talked about, that derivative is inverse of integration. Now, these are some of the mathematical preliminaries we have seen. Let us now come back to mechanics. So, a small break which we took, but we require all this, so that is why we have done. Now, so we come back to mechanics and physics, and we talk about kinematics. Let us start with definition of a particle. In our initial discussion on mechanics, we call it as particle mechanics. Particle is an entity of very small size, which means we will idealize this to be a point, but of a finite mass. So, such an object, what we call, we treat this as a particle. Now, it may be if we look at it from a physical point, finding something which has a very small size may not be possible. And what we will see is, when we study mechanics, we will treat, often we would treat things like ball, which may be a cricket ball or a football. They can also be treated as a particle. So, when can we treat these things as a particle? If the distance moved by these entities, by the individual bodies, is much large as compared to its size, and we assume that everything in there is moving like a same point. So, then we can treat these as particles. So, here what we have is that if we need overall estimates of path moved by the body without bothering about details of different parts of the body, then we can treat this body as a particle, and the distance moved by the body has to be much larger than the size of the body. Now, we also define another term when we study physics, is a rigid body, and rigid body is a body in which distance between any two particles is always the same. For example, if we look at a rubber band, and if I stretch a rubber band, I mark 2 points on a rubber band. When I stretch it, then I find the distance between 2 points, these 2 points will change. So, a rubber band cannot be treated as a rigid body. Whereas, if I look at a cricket ball in motion and I mark 2 points on the cricket ball. Now, as the ball moves, the points may move, but if I look at the distance between any 2 points on the ball, that will always be constant. So, that is what we call as a rigid body. Now, whenever we talk of mechanics here, we are talking of motion of a point, and to observe how a point moves or how it is moving, we require a concept of what is called a reference frame, sometimes also called as a frame of reference. It is very important to understand this concept. In a reference frame is a location on which distance between 2 points is always constant. So, for example, if I am standing on the ground, then I will say ground is a reference frame, and if I look at any 2 points on the ground, the distance between them will not change. So, this is how I define a reference frame, and in a reference frame what I do is I have a device with which I measure the length, and I have a clock with which I measure time. So, there are two things which I will need along with the frame, that in a reference frame we have a device to measure length and a device to measure time, which typically would be a clock. So, now when I fix myself on a reference frame and I want to observe, so now I can observe the motion of a point P in this reference frame. So, let us say this is the ground, there is a person here, I sit down here, I have and there is a point P, this point is moving with time. So, at time t is equal to 0, I measure the distance of point P with time, and I keep on measuring how P changes with time. I have an instrument to measure the length and I have an instrument to measure the time. So, using this I can see observe the motion of point P, and this is this motion has been observed with respect to reference frame 1. Now, the motion of the same point can be observed with respect to a second reference frame. So, reference frame, there can be multiple reference frame. So, let us say we have a reference frame 1, which is the ground, and on the ground suppose a car is moving. So, we observe the motion of the car with respect to ground. So, that is what I will say. I am observing with respect to reference frame 1 or with respect to ground, I see motion of the car. Now, let my reference frame 2 be the car. That means there is another observer, someone sitting on the seat of the car. So, now to the second observer who is sitting in the seat of the car, whatever is there in the car is not moving at all, whereas a person who is on the ground, so let us think of this. So, what we have is, suppose a car is moving, we have a car is moving on the road, reference frame 1 is on the ground and reference frame 2 is attached to the car. and let us say there is a point, a point on the rear seat of the car. Now, if I observe this from reference frame 1, now one thing what I will have to do is, if I want to observe the motion of a point P, what I will do is I will attach a coordinate axis to the reference frame 1, to the reference frame where I want to take measurements, and suppose I attach coordinate axis to reference frame on the ground, and I observe the motion of this point P, which is on the rear seat, a fixed point P. What I will find is, as the car moves, if the car is moving along a straight path, I will observe this point P to be moving with the car. Whereas the second reference frame, let us attach the reference frame 2 on the car itself, and let the axis be mounted on the front seat of the car. Now, from there, from this reference frame, when I observe the same point P, then I will have to go in the negative side because I am sitting on the front side. But if I look at the position vector P in reference frame 2, then as the car moves, I am moving along with the car, and in this frame what is going to happen is that the point P will appear fixed, whereas the point P appears moving from reference frame 1. And we have looked at the point P. If suppose I look at a point Q which is fixed on ground, then the point Q from reference frame 1 will not be appearing to be moving at all. Whereas if I look at this point Q from the car, then as the car moves, the point Q will appear to move. So, point Q, which is fixed with respect to reference frame 1, is moving with respect to reference frame 2, and point P, which is moving with respect to reference frame 1, is fixed with respect to reference frame 2. So, therefore, defining a reference frame, all these measurements which we take of the position vectors are always with respect to a reference frame. Now, let us pause a bit and think about this. Is there any reference frame which is absolutely stationary? That means, now we are talking of the reference frame. Can we find a reference frame which is not moving at all? So, in the example which I took earlier, it seems to us that if I have fixed the coordinate axis to ground, then in that reference frame nothing is moving, which may be good for some practical observations, but actually if you see, the earth itself is rotating about its own axis. So, therefore, if we have clearly, if we see a reference frame fixed to car, this is moving with respect to ground. Now, I take a reference frame which is fixed to earth or fixed to the ground. Then, in an absolute sense, this reference frame is rotating with the earth. So, that means even this frame is moving. So, then what I say is, maybe I fix my reference frame not to the earth, but to the center of the sun. If I do that, then in that frame earth will move, but this reference frame will not move. But sun itself is moving around some other body. So, therefore, whether it is possible to find a reference frame which is absolutely stationary, we do not know the answer. But the question is, why do we talk of stationary reference frames? And the reason for that is that later on we will talk about Newton's laws of motion, where we will relate force to acceleration, and that relation is valid provided acceleration of a particle is measured with respect to a frame which is stationary, which we also call the inertial frame of reference. If acceleration is measured with respect to some accelerating frame, Newton's law is not valid. And so, but then if we have said that if we do not know absolutely stationary frame exists, that means Newton's law may never be valid. But then the issue comes, can we treat the motion to be negligible? For example, in most of the calculations which we do for motion of bodies on earth, if we neglect the rotation of the earth, that works out to be a fairly good approximation. So, therefore, then we treat the ground as an inertial frame or as a fixed frame. But if motion of earth has to be accounted for, then this frame cannot be treated as inertial. So, these sort of considerations one have to keep in mind. So, now having observed a reference frame, what I am going to do is, before I start the discussion on kinematics of a simple discussion on kinematics of a point, I would like to give a basic definition of two quantities which will come in, which are velocity and acceleration. We talked of motion of a point. Now, velocity of a point will give us an idea, we will come to the exact details of what velocity means later, but it gives us an idea of how fast a point is moving. A moving point means its distance is changing with time. How fast is this distance changing? That idea is what is given to us by velocity. And I will talk of in a moment about the exact meaning of what we call as the velocity. And similarly, how fast the velocity is changing with time, this notion is what we understand by acceleration. So, velocity and acceleration give us rate of change of distance and rate of change of velocity respectively. So, now let us see, we are again taking planar motion in this case. Suppose this is a path on which point P is moving. So, at time t, the point or the particle is at P, and this is the origin. So, what we do is we draw OP is the position vector at time t, we denote it as vector r as a function of time. At time t plus delta, so this is at time t, at time t plus delta t, the particle is at p prime. So, the position vector is given by OP prime. This vector is the position vector at time t plus delta t. So, this is r at t plus delta t, this is r at t. Now, the vector p prime, this is called as the displacement vector. And if I look at r vector at t plus delta t minus the r vector at t divided by delta t, and the limit that we keep on making delta t very small, in the limit delta t goes to 0. This is what we call as the velocity vector at time t. That is the basic definition of velocity vector. So, the velocity of point P at time t, this is the velocity vector, this is equal to the derivative of the position vector. I am giving you very general definition here. We have not even talked about the how do we add or subtract vectors, that will come in later. But before we move on ahead, at least let us go through the general definitions. So, we have the position vector P, position vector P prime. So, we look at the displacement vector between these two. Now, one thing you will realize, and this is again some thought which I would like to leave with you, that if there is another set of axes on the same reference frame with which you are measuring this, and that axis could be oriented anywhere. In that set of axes again, if you look at the vector p p prime, that will be the same. The position vectors in the new, so for example, if there is, let me use a red pen here. So, suppose there is another coordinate system, let us say x prime y prime, mounted on the same reference frame. The origin is different, the directions are different. Now, if I look at the position vector of point P, position vector point P prime, they are different from r and r at t and r at t plus delta t. But if I look at the vector p p prime, this is the same even in the new coordinates, and the velocity is given as p p prime vector divided by delta t, limit delta t going to 0. So, therefore, the velocity vector will be the same, it is independent of the coordinate axes, provided they are both fixed on the same reference frame. If they are fixed on the same reference frame, even if the origin or orientation of the coordinate axes are different, the velocity v of the point will be the same as a vector, because that just depends on p p prime, which is the same whether it is measured in x y or x prime y prime. So, this is the definition of velocity of a point P, and I will just give the formal definition of acceleration. These definitions are general and they will work for one dimensional, two dimensional, all of motion. So, acceleration of point P, this is given as velocity of point P at t plus delta t minus the velocity of the same point P. So, this is, you could call it as P prime, because that is what we call it is the same point actually. So, P and P prime are just different locations of the same material point. So, and divided by delta t, in the limit delta t goes to 0. If we take the difference between the two velocity vectors, then we get acceleration of point P, and which in terms of our starting definitions we will call it as instantaneous acceleration. So, with these concepts we would like to move on to the concept of the simplest type of kinematics, which is motion in a straight line. So, now what we look at is a particle moves along a straight line. So, we have some line like this, we have a particle which we say is P, it moves at different location. Now, it need not move forward only, maybe after some time it can recede its path. So, this is the particle P which is moving along a straight line. Now, what we can do is we can align the x axis along the straight line. So, for example, the particle could be moving like this. If it is moving, it may look inclined, but what I can do is I can always align my x axis in this direction along that incline, as long as it is moving in straight line. So, then what we will have is the particle, when it moves along a straight line, we can generalize it by saying it travels along x axis or minus x axis. So, we will tilt, and this is called rectilinear motion, and this is as opposed to curved or planar motion, which will come if the particle is, let us say, going along a curved path. Now, in rectilinear motion, the position is the location in space where the particle is at time t. So, as the particle moves, then we also, so for example, suppose if this is the path, so at time t is equal to 0, the particle is here at, let us say there is a distance of 200 meters, this is point P, this is point Q which is at another 100 meters from P. So, at time t is equal to 0, the particle is at O, at time t is equal to 1 seconds, particle is at P, at t is equal to 2 seconds, the particle is at Q, and at t is equal to 3 seconds, particle is at P. That means the particle moves from O to P, P to Q, and then comes back to P. So, if we write what we call as the path length, let us write the path length. Path length is the total distance which the particle moves, or the length of the path. So, now at t is equal to 1, so path length is the distance, let us find the path length. Of this particle. So, what we find is, if we try to find the path length, at t is equal to 1, the path length is 200 meters. At t is equal to 2, the path length moved is 300 meters. And now comes the thing, at t is equal to 3, the particle has moved 200, 100, and then it comes back from Q to P. So, that means it has moved another 100 meters. So, the path length is equal to 400 meters. So, path length is the scalar distance moved by the particle, and this has no direction. This quantity is always positive, because when a particle is moving, it covers a distance, and as much distance as it covers, it is always positive. Now, path length is opposed to what we call as quantity called displacement, which is the net change in x position. So, suppose if the particle is at coordinate x1 at time t1 and is at x2 at time t2, then displacement is defined as delta x by delta t. The symbol delta which I have used here, this means the change in, which is x final minus x initial. So, this will be equal to x2 minus x1 divided by t2 minus t1. So, this gives us the displacement, and if x2 is greater than x1, that means the particle is moving along the positive x axis, and if x2 is less than x1, the particle is moving along the negative x axis. So, if the particle is moving forward, so displacement can be either positive or negative. So, displacement can be positive or negative. It is positive if particle moves along the x axis and it is negative if particle is moving against the x axis, or it is moving, as we would say, along the minus x axis. It is moving in the minus x direction, then we say this is displacement. So, now displacement is a vector quantity but in one dimensional motion we do not need to give its direction, in the sense that it is always along x. So, therefore, in 1D motion direction of displacement is given by the sign. If displacement is positive, then it is along plus x axis, and if it is negative, then it is along minus x axis. So, this is how one writes the displacement as a vector, and it is clear from here that displacement is not the same as path length. They are two different quantities. So, in the next class we will continue from here. We will talk about how we look at the graph of x versus t, what is the meaning of those graphs, and we will then talk about how fast a particle is moving. That means, we will introduce the concept of velocity and how fast the velocity is changing, that is acceleration, for one dimensional motion in the next class. Thank you.